It's time to learn about Lesson 3.8, which is going to be on inverse functions. For this lesson, you're going to need one note card, and you're also going to need your video notes paper that I provided for you. So I want to start by saying that this is another of the concepts that you learned about in Algebra 2, but I'm pretty sure that all this idea of the inverse of a function might have been a little bit fuzzy for you, or maybe you didn't understand exactly what you were doing or why you were doing it. It kind of got thrown at you at the beginning of the year in Algebra 2. So I want to go back through all of the ideas for finding an inverse and then checking to see if the inverse is a function, and then also talk to you about some of the ways that we can use the graph translation theorem and what we've been studying to determine whether we're going to be able to find an inverse that is a function. Okay, so to start, we're going to start with the idea of when coordinates are switched. So here we have a set of ordered pairs, and the set of ordered pairs contains negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. And it says, can we find the inverse of f? And absolutely, we can find the inverse of f, because when the coordinates are switched around, the result is the inverse of the function. So all the ordered pairs x comma y are going to become y comma x. That's how we're going to form the inverse. The inverse is a special symbol. It looks like f to the negative 1 power, or the negative first power, but it stands for f inverse. F inverse. So when you have a set, all you do is switch the ordered pairs around. So you'd have 9, negative 3, 4, negative 2, 1, negative 1, 0, 0, 1, 1, 4, 2, and 9, 3. Notice we started with 1, 2, 3, 4, 5, 6, 7 ordered pairs. We still have 1, 2, 3, 4, 5, 6, 7 ordered pairs. We just switched the coordinates around. We want to know if the inverse is a function. So to determine when you have a set of ordered pairs whether or not you have a function, you look at all the x values, and you check to see if there are any repeated x values. So when we look at all the x values, we see, well, yeah, we have 2 9s, we have 2 4s, and we have 2 1s. Even if we just had any two numbers that were the same, we wouldn't have to have 3 pairs of them that were the same, but any matching numbers in the x would cause this to not be a function. So is the inverse a function? And the answer to that is no. The inverse is not a function. Okay, we want to talk about what one-to-one means. You know we have the vertical line test to determine whether an equation represents a function. So if we want to know if something is a function, we pass a vertical line through it that never touches more than one point at a time, then it is a function. Well, the horizontal line test, and you might remember that from last year, we called it the HLT. It's used to determine if a function is one-to-one. And what that means is, if a function is one-to-one, then it has an inverse that is a function. If a function is not one-to-one, in other words, it does not pass the horizontal line test, it will still have an inverse, because we can switch the ordered pairs around, but the inverse will not be a function. All right? So a lot of times we only want to study those things that are one-to-one and pass the horizontal line test, because it's only interesting to study something that's inverse is also a function. Okay, well, let's look at these and we'll see which ones of these are one-to-one. In other words, we want to ask ourselves, does the graph pass the horizontal line test? That makes it one-to-one. Well, if I made a little sketch of f of x is equal to x squared, that is the parent graph of the parabola, isn't it? Okay, well, the parent graph of the parabola would not pass the horizontal line test. So when the question is, are these functions one-to-one, this one is a no, because it fails the horizontal line test. I can still switch all the ordered pairs around and form a function, but the function will not pass the VLT. So if I took this function and I switched all the ordered pairs around, it would make a parabola lying on its side. And that would not pass the vertical line test. So this inverse of this parabola is not a function. Okay, let's think about 2x minus 1. 2x minus 1 is a line. It has a y-intercept of negative 1 and a slope of 2. It's going to look something like this. Would this line pass the horizontal line test? And the answer is absolutely it would. All right, so is this function 1 to 1? Yes, it is. Okay, and if I'm looking at 4 minus x squared, 4 minus x squared, and maybe a better way to write that would be minus x squared plus 4. So that's going to be a parabola. It's been moved up 4, and it opens downward. So it's going to look something like this, where this is going to be 0, 4. Well, once again, does that parabola pass the horizontal line test? And the answer is no. So it's not a one-to-one function. It's not considered one-to-one. Here are some properties of inverse functions. If f inverse exists, then f inverse is a one-to-one function. Okay, so the inverse would pass the horizontal line test. The domain of f inverse is the range of f, and the range of f inverse is the domain of f. And that's because for every ordered pair x comma y, we are switching it to y comma x. So we consider the x's the domain values and the y's the range values. So when we switch those around over here, this domain becomes the range, this range becomes the domain. That's what that means. Okay, well, we're going to go through a procedure for finding f inverse, which is the inverse of a function. Okay, we're going to go through the procedure for doing that. And so I want you to write this on your note card. So let me pull this up here. This is going to be our procedure, all the steps that we're going to follow every time we want to find the inverse of a function. So we're going to entitle this note card 3-8, inverse of a function, and then we're going to write finding f inverse of x, the inverse function. Okay, so the number one step is we're going to ask ourselves, is the function 1 to 1? In other words, does the function pass the HLT, okay, the horizontal line test? So that's the first question you want to ask yourself. Does it pass the horizontal line test? If the answer to that is no, then the inverse function does not exist. Remember, everything has an inverse. I can switch the ordered pairs around, but it will not be a function. It will not be a function when I get done. It'll be like that parabola lying on its side. Okay, if the answer is yes, we're going to find the domain and the range, and we're going to write them down. So the first thing we're going to do is write down the domain and the range. Okay, the next step is number 2. We're going to replace f of x with y in the equation. Then we're going to switch the x and the y in the equation. Switch them around. Then we're going to solve for y and replace y with f inverse of x. And then we're going to write the new domain and the new range beside f inverse of x. The range of f of x is the domain of f inverse. The domain of f of x is the range of f inverse. Because the idea here is we're going to switch the ordered pairs x comma y into y comma x. If you need to pause this video right now, you can, so that you can finish writing all these steps down. But these are the 5 steps that we're going to follow over and over and over again for all the different kinds of functions that we're going to do. Okay, so the next thing I want to do is I want to move on to the video notes page. And I want you to work with me here, fill this in, and we're going to find the inverse of a function if it exists. So it says on numbers 1 through 4, we're going to follow all of the steps. Actually, I think there's 6 of them. So on 1 through 6, it should say. We're going to follow all of the steps on our note card that we just made for finding f inverse of x if it exists. Okay? And so we're going to start with number 1. Now, I also loaded up my calculator here because I'll give you a couple of options. You need to have some kind of a visual in order to see whether it's going to pass the horizontal line test. So you can either graph it on your calculator and look at it, or you could just know what it looks like and you could graph it by hand. If you're good at sketching and using the graph translation theorem, I think that you could probably do that pretty efficiently. So number 1 says we're looking at f of x as 1/3 x plus 4. So I'm going to draw a little picture of what that would look like. Okay, that has a y-intercept of 4 and a slope of up 1 over 3. So the line looks something like this, doesn't it? Okay. All right, so you ask yourself, would that pass the horizontal line test? And the answer to that is, it most certainly would. So the next step on our note card says we're to write down the domain and the range. So we're going to write the domain and the range of this original function here. The domain is all real numbers, and the range is all real numbers. Okay? Now the next thing we're going to do is the next step on the note card. And it says you're going to replace f of x with y. So we're going to write y equals 1/3 x plus 4. Now we're going to switch the x and the y around. So x is going to equal 1/3 y plus 4. Just simply switching x and y. The next step says we're going to solve for y. So to solve for y, we want to subtract 4. And we'll wind up with x minus 4 equals 1/3 y. Then to get rid of 1/3, we're going to do the inverse operation of that. We're going to multiply by 3. So we're going to multiply this by 3. So we wind up with y equals 3x minus 12. And then we're going to rename that f inverse of x. That's step number 5. To write f inverse of x equals 3x minus 12. And then we're going to do the new domain, which is the old range. And the new range is the old domain. Okay, so all of this is our answer. If I was checking this problem for you, I would first check to see if you wrote down the original domain and range. Then I would look at all of your work, and then I would look at your end result over here. Okay, now what I want to do is I want to go ahead and graph 1/3 x plus 4 over here. And then I want to graph 3x minus 12. Alright, and I want to just, I'll just put those on a Zoom 6 window so we can look at them. So here's our original function. Here's the one that we found to be the inverse. Alright, inverses are reflections. Inverses are reflection images over the line y is equal to x. And that's because we're switching our x and y coordinates around. So if I were to take this and say, graph for me the line y equals x, I'll put that on there as my mirror line. Does it look like, let me make one of these thick. I'll make the second one thick. So here's my original. Here's my inverse. Does it look like the thick one is the reflection image of the thin one over the line y equals x? And I think it does. It looks pretty good. Another good window for this is the square window. It's kind of squared up. And maybe you can see that better. But here's the original. Here's the one we said is the inverse. And sure enough, they're reflection images of the line y equals x. Okay, let's try number 2. What would number 2 look like if we made a little sketch of it? Well, if we made a little sketch of it, it's a square root function. And the minus 4 is moving it 4 units to the right, isn't it? So it's going to look something like this. And this is going to be 4, 0. Alright, would that pass the horizontal line test? And the answer is, absolutely it would. Alright, so we want to write down the domain and the range of this. The domain of this, the lowest x value is 4, but it proceeds to the right. For the range, the lowest y value is 0, and it goes to the right from there. Alright, we're going to replace f of x with y. Then we're going to switch our x and y around. and then we want to resolve for y. Right now, y is trapped under that radical symbol, so in order to get it out from under the radical, we need to square both sides. So we wind up with y minus 4 equaling x squared, don't we? So that means y is equal to x squared plus 4. We're going to move this 4 over here. So that means f inverse of x is equal to x squared plus 4. The new domain is the old range. That would be 0 to infinity, the old range. The new range is the old domain, which is 4 to infinity. Now, this is what we know about this. We know that the inverse of this function is not going to be this whole parabola, is it? But we're only starting at 0, 4, and we're going up from there. So we would be saying that the square root would reflect itself over the line y equals x, and it would become this branch over here. And that's what it would look like. So that works pretty slick. That's a great reason for writing down the domain and the range original, because you have to switch those when you get them down to here. So all of this is your answer, along with this and all the work that you did. Okay, let's try number 3. Number 3 would be a parabola that's been moved down 4. So would it look like this if this is 0 and negative 4? Okay. Does that pass the horizontal line test? Well, no, it doesn't. So this one is not 1 to 1, because, and then we're going to say that the inverse function does not exist. Okay, not that this doesn't have an inverse, because it does, but the inverse is not a function. Okay, let's try number 4. What would number 4 be if we graphed it? Well, number 4 would be a hyperbola, wouldn't it? And it would be a hyperbola that's been moved 3 units to the left. Okay, so we're going to go over here 3 units to the left. And we're just going to draw a little hyperbola on here. The 4 would just be to stretch it. Alright? And so the domain of this function, by the way, this passes the horizontal line test. The domain would be all real numbers except negative 3. That's my vertical asymptote. And the range would be all real numbers except the degree of the numerator is less than the degree of the denominator, so the horizontal asymptote is at y equals 0. Okay, so we can do this problem. We're going to say y is equal to 4 over x plus 3. So x is equal to 4 over y plus 3. Okay, now there's some different strategies that we could use to solve this problem. But I don't know if you've ever thought about this or not. You can do the same operations on both sides of an equation. For instance, if I had an equation and I had y plus 2 equals x, I can add or subtract the same number on both sides. If I have a multiplier, 3x equals 10, I can divide both sides by the same number, or multiply both sides by the same number. Well, something else that I can do in this particular problem when I want to solve for y is I could turn these both into fractions or make it look like a proportion, and then I can invert both of these fractions here. So I could say 1 over x equals y plus 3 over 4. Notice how the cross products didn't change. They have the same value when you do the cross product. Okay, so that means that once I get that done, I would have multiply both sides by 4. So 4 over x equals y plus 3, and then we'll subtract 3 on both sides. So we're going to say f inverse of x is equal to, there's more room here. Okay, it's going to be equal to 4 over x minus 3. The new domain is the old range. which works out perfectly because the only number I can't have here is 0. The new range is the old domain. And that makes sense because I'm going to move this function down 3, aren't I? Okay, so that's pretty cool how you can do that. You might want to put a little star on that one because you'll be seeing some more hyperbolas and you can just reciprocate both sides. Okay, number 5 is another hyperbola, isn't it? This time the hyperbola has been moved 4 units to the left. Okay, then we have a stretch of 5, so it's just going to cross up here and over here. This is -4. Okay, does it pass the HLP? Sure does. So the domain of this is all real numbers except -4. And the range is going to be all real numbers except 0. The degree of the numerator is less than the degree of the denominator. That's case A on our note card, isn't it? So if y is equal to 5 over x plus 4, and x is equal to 5 over y plus 4, switching our x and y around, I'm going to make this into a fraction. I'm going to flip both parts of it. So 1 over x equals y plus 4 over 5. That's kind of a quick way to get your y variable in the numerator, get it out of the denominator. Okay, the next step will be to multiply both sides by 5. That'll give you 5 over x equals y plus 4, and then we'll subtract 4 from both sides. So we're going to have f inverse of x is equal to 5 over x and a -4. 5 over x and a -4. Now, the new domain of this is the old range. Obviously, you can't have 0 there. The new range is the old domain. And there we have it. Okay, the last one we're going to look at is the absolute value of x plus 3. An absolute value graph with a good grouping symbol. The absolute value bars are a grouping symbol. Says that the parent graph is being moved 3 to the left. So it'll look like this, won't it? And this will be -3, 0. Okay, does that pass the horizontal line test? And the answer to that is no. Okay, so this function is not one-to-one. And so we're going to say the inverse function does not exist. It has an inverse, but the inverse is not a function. The inverse is not a function. Okay, so you're going to get to play around with all kinds of little examples of anything on that pink note card, any of those parent graphs, any version or variation of those parent graphs, and you'll be able to determine that some of them are not very cooperative on being one-to-one, and others are, and then you can find the inverse function for some of them. Okay, now another little thing we're going to work on is determining whether a pair of functions are inverses by finding their composites. If we find f of g of x and we find g of f of x and they're both equal to x, if they're both equal to x, then we would say that the functions are inverses of each other. If they're not both equal to x, then the answer to that is no. All right? So we're going to start with number 7, and we're going to find f of g of x. That means we're going to put g into f, aren't we? Put g into f. If I put g into f, I'm going to have 1/2. I'm going to replace x with 2x minus 4, and then say plus 2. And then we just need to simplify this. The distributive property says we're going to get x minus 2 plus 2, and that's going to equal x. So we're halfway home. The first composite is equal to x. Then we need to look at g of f of x, which means we're going to put f into g. So we're going to take this and put it into g. To do that, we'd have 2 times 1/2 x plus 2 and a minus 4. So 2 times a half x is 1x, then plus 4 on our distributive law, minus 4, and that's equal to x. So if this both equal x, each composite with each other is equal to x, we would say, yes, the two functions are inverses. What does that mean? That means that if I change this to 1/2 x plus 2, and if I have this one be 2x minus 4, then I graph my first line, I graph my other line, and here's the line y equals x, and each one is the mirror image of the other over the line y is equal to x. Okay, let's try number 8. Let's do f of g of x first. Okay, so we're going to put g into f. 3 times 1/3 x minus 6 plus 9. 3 times a third would be 1x minus 18 plus 9, and that's going to wind up equaling x minus 9. Okay, let's try g of f of x. That means we're going to put f into g. Alright, so we'll have 1/3 times 3x plus 9 minus 6. So x plus 3 minus 6, which equals x minus 3. What do you know about these? They are not equal to x, are they? They're not equal to x, and we're going to say that these are not inverses. Okay, not inverses of each other. No, they're not inverses. They're not inverses. Okay, let's try number 9. Number 9 says, okay, if I wanted to do f of g of x, then I'm going to put this in for x right here. So it would be 3 over x. Okay, that means 3 divided by 3 over x, which is the same thing as 3 times x over 3. These 3's are going to cancel, and that's going to equal x, isn't it? If I do g of f of x, that means I'm going to put this f down here. I'll have 3 over x, which is still 3 divided by 3 over x, which is still 3 times x over 3, which then equals x. Each one composite with the other is giving me x. So what does this tell me? This tells me that, yes, the two functions are inverses. That's what they are. They are inverses. All right. That's kind of the long and the short of inverses. I'll give you some experience with those again tomorrow in class, when you come back to class. And we'll also explore a few other things with the domain and range and different kinds of functions. All right? Have any questions? Please let me know.